So today I'm going to talk to you about some work that my collaborators and I have been working on for the last 3 years now. So this was joint work with a bunch of people who are now spread across a few different universities, but it started at the University of Illinois. So Shailesh Venkatakrishnan, Surya Bakshi, Brad Denby, Shruti Bhargava, Andrew Miller, and a lot of you have probably heard in the news stories about Bitcoin being portrayed as this untraceable currency. So of course, as you all know, I mean, I'm preaching to the choir here, but Bitcoin is not totally untraceable. There's a lot of different ways that Bitcoin users and transactions can be de-anonymized. But so in this talk, I'm going to focus on one particular avenue for de-anonymizing Bitcoin transactions, which is the peer-to-peer network. So you got a great primer this morning from Suhas on how the Bitcoin peer-to-peer network works. So for the purposes of this work, I'm going to use kind of a very simplistic representation of how the network works. So in particular, the problem here is that users in the Bitcoin peer-to-peer network have two identities. The first one is their public key that they're using to sign transactions. The second one is their IP address. And to a large extent, anonymity depends on not being able to link your public key to your IP address. So whenever Alice wants to send money to Bob, the first thing she does, of course, is to create a transaction message, which is going to get broadcast over this network until all the other nodes hear about it and can start mining to add it to the blockchain. So what about this allows users to be de-anonymized? So typically when we talk about anonymity problems in the Bitcoin blockchain, people are talking about chain-level attacks. So basically, because the Bitcoin is just a ledger of every transaction that's ever happened, you can often link together different transactions coming from the same user. And you can start making these kind of graphs that connect together the same user doing multiple transactions with different parties. And if you know who certain parties are, like if you know that this big purple guy is Mt. Gox, you might be able to narrow down the set of users who are interacting with Mt. Gox. So this is typically what people mean when they talk about the privacy vulnerabilities in Bitcoin. And because a lot of people are reusing public keys, in some cases this means that entire transaction histories can be revealed. So this was kind of the state of the art in privacy research or privacy understanding in Bitcoin for a while. But more recently, people have started looking at the peer-to-peer network and how do the relaying protocols in peer-to-peer networks affect your privacy guarantees. So the goal in our work was to try to understand how easy or difficult is it to link a public key to an IP address. Those two identities that we talked about earlier. So in our work, we basically had two main components. The first one was analysis. So we tried to understand how existing broadcasting mechanisms allow an adversary to infer the source of a transaction based on just observing the spreading patterns in the network. And the result of this was basically that it's pretty bad. So in many cases, an adversary can identify who is the source of a particular transaction. The second part of the talk is going to be on trying to come up with a better design for how to broadcast transactions to try to mitigate this privacy vulnerability. That's a project called Dandelion that I will talk more about later. So so in this talk, I'm going to do something a little different from what I usually do, which is to focus a little bit more on the actual process of doing this research and on some of the decisions that we made from a researcher standpoint. So usually when you hear a talk, you hear people say, okay, this is the problem we set out to solve. We sat in a room, thought really hard, and bam, it's done, it's solved. And of course, that's not really how research goes. Often it's very roundabout. You don't know ahead of time what you're going to be able to do, what you're not going to be able to do. And you have to make a lot of decisions and compromises. So I'm going to talk a little bit about some of those decisions and compromises that we made and how they affected the final end result. So a big part of that, big part of those decisions is in coming up with the model that you use to analyze your problem. So anytime you want to do theoretical analysis, you always have to come up with a model for the system that you're trying to analyze. And one of the big challenges that often arises is that if you want to be able to say anything conclusive theoretically, your model has to be simple enough to be analytically tractable. But if it's too simple, then it no longer represents the system that you're trying to model. So there's always this tension between trying to pick a model that is not necessarily perfect, but representative enough of what you're trying to get a hold of. Privacy in particular is, privacy and security are two areas where theoretical analysis is particularly important because for topics like efficiency, for example, it doesn't necessarily matter if you have a theoretical proof that it's efficient. Like if you know that it works in practice, if it's efficient in practice, it's efficient. But with things like privacy and security, you might not know that it's broken until something really bad happens, right? So that's the reason that it's particularly useful for privacy and security problems to have some kind of theoretical proof, so that you know the worst possible adversary can't do more than this. And of course, the flip side of that is that your guarantees are only as good as your models. So if you're able to prove some great result under a model that's really restrictive, it's not that useful. Okay, so we started this project after reading some papers from the security literature. And these papers basically had the following structure. They were saying, let's suppose that we have our peer-to-peer network, and we have an eavesdropper, a supernode, that sets up connections to everybody. And the purpose of this eavesdropper is to try to figure out which node originated a particular transaction. So now, when Alice starts broadcasting her transaction, she sends it to all of her regular peers, but from her perspective, this eavesdropper looks the same as anyone else, so she'll also relay it to the eavesdropper. And her peers also relay to the eavesdropper and so forth. So everyone is treating this eavesdropper as just any other node. Now, if I'm the eavesdropper and I want to try to figure out who is the source node, a really natural thing for me to do is to wait for the first node that relays a transaction to me and say, okay, I think you're the source. Now, this doesn't always work. Can anyone think of why this might not work all the time? Yeah. Oh, sorry. No, sorry.
Network conditions.
What do you mean?
Like a packet might get dropped by a route in the middle and then it gets sent later, so the timing is not as you would expect it given the distance between you and the server. Right. So the key essence of what you said is that there's the timings are not always deterministic. So in particular, in this diffusion spreading mechanism that Suhas talked about earlier, remember that you're relaying messages to your peers with some random delay. So what could happen is Alice could send her transaction to Bob, and Bob could forward it to the eavesdropper before Alice herself does. So in that case, if I'm the eavesdropper and I'm just pointing at the first node that relays it to me, that's not always going to be 100%. So what can the eavesdropper do about this? Well, in these security papers that we were reading, the approach that they took was to set up a bunch of mini eavesdroppers. So let's say we have like one eavesdropper on each port that the adversary is running. And each of these mini eavesdroppers makes a connection to each of the nodes in the network. So now what do we have? We have spaghetti. But the point is that if Alice starts broadcasting her transaction now, 3 out of 5 of her connections are to the adversary. So with probability 3/5, the first message that she sends is going to end up. So the adversary can get more and more accurate by making more and more of these connections to each node. So, yes?
But there can still be a possibility that there is a different node that has better connection, and going through him might physically be faster than going directly to the adversary.
That is true. So here we're kind of imagining that all of these links are created equal or the same speed, which might not be true.
But isn't the actual Poisson delay is significantly higher than what you might imagine network latency to be?
It's true. That is also true. Yeah. So the Poisson delay is on the order of seconds, which is going to be a lot faster than, or a lot slower than changes in network. If you have two exponential delays that are roughly the same, then network latency might play an effect. But I think that's going to be probably a second order. So to try to capture this, we made an adversarial model that is summarized by two parameters. So the first one is theta, which is going to be the number of connections that the eavesdropper makes to each of the compromised nodes. Okay, so here theta is equal to 2. The second parameter is going to be p, which is the fraction of nodes that are being eavesdropped on. So in the previous examples that I showed you, p was equal to 1. So the eavesdropper had connected to everyone. But in principle, you could imagine an eavesdropper who's only connecting to some fraction of nodes in the network. So our adversarial model has these two parameters, p and theta. And in our work, we focused on two main operating regimes in this adversarial model. The first one is where p is equal to 1, so the eavesdropper is connecting to everyone, and theta can be arbitrary. It's anywhere from 1 to infinity. And this is capturing basically this eavesdropper model that we read about in the security papers. The second adversarial model that we considered is where p is less than 1, but let's say that the eavesdropper has infinitely many connections to each node. So it's as if the nodes themselves are corrupt. So we call this the botnet adversary, and this way of framing it as an eavesdropper is really just a mathematical abstraction. Really, we're thinking of these nodes as just being themselves corrupt, and they're part of some colluding botnet that is trying to de-anonymize people. So in this work, we started our analysis of de-anonymization on the eavesdropper adversary, and then ended up actually designing Dandelion to be robust against the botnet adversary. So here, I'm going to deviate from how I usually give this talk and explain a little bit more. This is a little funky, right? We're changing the adversarial model. We're analyzing the problem under one adversarial model and trying to fix it in another. So what happened here was that once we figured out there was a problem with the eavesdropper model, it turned out to be actually pretty easy to fix that problem under the eavesdropper. So here's a kind of a distinction that arises in academic research that might not happen if you're in industry and trying to research some of these issues. So in academia, we care about solving impactful problems, but we also care about publishing papers. And so, like if your problem is too easy, it's not going to be publishable. So that was part of the motivation for going to this botnet adversary, because we felt that this was still like an important problem, but it was a little bit more challenging and required a little bit more mathematical machinery. So we felt that it would be a better fit for academia. So in your case, you probably won't have run into these kinds of considerations, but it's just something to be aware of if you are working with academics or in this space. Okay, so let's start out with part 1 on analysis. So are there any questions so far on the model? So analysis, how bad is this problem? Here I should give a little bit more background, and so Suhas touched on this earlier. Now, up until about 2015, the peer-to-peer network was using a broadcasting mechanism called trickle. And here I made a very stupid mistake that I hope to convey to all of you so that you don't make it as well. So I read about trickle in one of these security papers, and the lesson here is that you should never try to understand a protocol just from somebody else's description of it. You should read the code. So I misunderstood how trickle was working from the description of this paper, and thought it was the following model. I thought that you arrange your neighbors in some random order. Let's say 1, 2, 3, 4. And then every seconds, let's say every 1 second, you send it to those neighbors, you send your message to those neighbors in that order. So it turns out this is a little bit off, and we actually got an email after putting this paper on arXiv from Greg Maxwell being like, hi, I don't think you completely understood this correctly. So my understanding, and I guess there's people in this room who know this much better than I do, but my understanding is that what was actually happening is at each time slot, so like if we're waiting 1 second between each communication, at each time slot you pick one of your neighbors uniformly at random and then send the message over that edge. Is that correct? Okay. So it's similar to what is happening here, but it's not exactly the same. So take these results with kind of a grain of salt. Okay, so this was done until about 2015, and then because of the privacy issue that Ross mentioned, they switched to diffusion. So under diffusion, on each of your edges, you take an exponential delay, or an independent exponential delay, and once that timer ticks, you send your message along that edge. And so we were looking at the GitHub logs, and it said that they were doing this for privacy reasons, but we didn't understand exactly what those trade-offs were. So the question that we tried to answer was, does diffusion actually provide stronger anonymity than trickle? And so notice here that even though the model of trickle is a little bit off, it's close enough that I think it's probably a pretty reasonable representation. So I don't think this is completely off. So, okay. So to answer this, we wanted to try to model the problem in some way that's analytically tractable. Now, one of the big challenges in analyzing random processes on graphs is that graphs are a pain to analyze. So if any of you have tried to do any analysis on graphs, getting results for general graphs is a big deal. Like, it doesn't happen very often. So typically what people will do when they're analyzing these kinds of processes is to start with a simpler topology that's easier to analyze. So for example, we started with deregular trees. So deregular trees are trees where each node has exactly d neighbors. And so we assume that like the honest connections are structured in a deregular tree. And then we have our eavesdropper that's making theta connections to the honest. So this is our graph topology, and here trees are actually a somewhat reasonable model for the Bitcoin peer-to-peer network, because in random graphs that are sparse, so like in Bitcoin, you can think of the graph as being constructed by choosing, like, let's say 8 outbound connections. You have a bunch of nodes. You have like thousands of nodes in the network, tens of thousands if you include all of the clients. So, so in these kinds of graphs that are constructed by choosing random edges in a sparse way, often it's been found in a lot of different cases that these graphs tend to be locally tree-like. What does that mean? That means if you look at one particular node and you look in a local neighborhood of it, it looks roughly like a tree. So trees end up being a pretty reasonable model for a lot of these types of analysis. And we found in our simulations that our predictions on trees were pretty close to what actually happened in simulations on the real Bitcoin topology. So that's one simplification that you could make if you were trying to do analysis on these kinds of problems. Okay, so yeah.
Is there some kind of intuition why they turn out to kind of look like trees? Because like a node goes online and the slots get taken and then the next one, and so on and so forth.
Good question. So the reason, if you think about it intuitively, let's say that every one of us is picking like 2 neighbors. So let's say I pick like you two. And I'm selecting you uniformly at random from the pool of everyone in this room. Now, if we look at the probability of either of you two picking me again, it's quite small. The dominant event here is going to be that you two pick somebody else. And that continues for a few hops. So basically, if you have enough nodes and everyone is picking only a few connections, you can show with high probability that locally you're going to get a tree-looking structure. Does that make sense?
Yeah, I don't think you can have outbound connection for the same incoming connection, right? It's usually just one way.
But she's saying even your child won't have your parent as a connection, probably.
Exactly. Okay, so this is our graph topology. The next thing that we need to specify when we're analyzing privacy is what metric do we want? So people have a lot of different metrics for privacy. For anonymity, we chose to analyze the probability of guessing the true source, conditioned on
Two pieces of information.
So the first piece of information that we condition on is tau, which is going to be the timestamps that the adversary observes. So our eavesdropper, from each of its
connections, it's going to get some timestamps as to when the message gets replayed.
We're assuming that the adversary sees all of that. The other thing that we're conditioning on is the topology of the graph.
The structure of the graph.
So remember, Suhas mentioned that it's actually, that like right now there's an ongoing effort to try to hide the structure of the graph, and that's supposed to be difficult. There has been some work, so like Andrew Miller has some work on trying to recover the graph's topology even if it's supposed to be hidden by basically placing conflicting transactions at different locations in the network and seeing where they spread to. If you do that a bunch of times, you can kind of recover the topology. So there have been some attacks on trying to recover the topology anyway, but so like assuming that the adversary knows the graph
is basically the worst case assumption. You're giving
the adversary the most
power.
All right, so that's the metric that we're analyzing. And finally, we want to understand what estimators should we analyze. Okay, so what is the adversary actually doing to try to
de-anonymize users?
So for this work, we analyzed two different types of estimators. The first one we call the first spy estimator. And so this estimator basically just looks at all of the timestamps reported by each of the nodes, and it picks the smallest one. So this is basically saying the first person who relays to me, I'm going to say that they're the source. So on this picture, I think node 4 has the smallest timestamp. So
it's going to be the estimator for the first spy adversary.
And the reason this is a useful estimator is because this is what's used in those security papers that I talked about earlier. It's a very natural, easy estimator to run. It doesn't actually require
any knowledge of the graph. Notice you can do this even if you don't know the underlying graph.
The other estimator that we look at has a lot more power. This is a maximum likelihood estimator.
So how many of you have, out of curiosity, how many of you have taken a class on like estimation and detection theory? Okay. How many of you know what a maximum likelihood estimator is? Okay. All right, good. So let's talk about maximum likelihood. Let's suppose that we're living in a world where there are two options. Okay, so let's say that those options, let's suppose that we know that transaction came either from Alice or from Bob. Okay, so we have two nodes, Alice. So let me write a little bigger so that people in the back can see. Okay, so we have Alice and we have Bob. And these guys are connected on the network in some way. And our adversary, remember, is observing timestamps from everyone. So our adversary has this vector, tau, of timestamps that everyone sent, at which the adversary received the message from each one of the nodes in this network. Okay, so here we have a bunch of nodes that are not Alice and Bob. So when we talk about the likelihood of an event, we mean the probability of seeing the observations that we saw
so seeing, let's say, tau, conditioned on each of the options that we're looking at. So the probability of observing tau conditioned on Alice being the source versus the probability of tau conditioned on Bob being the source. Okay? And we can compute these probabilities exactly because we know the graph and we know the random mechanism that's being used to spread the transaction. So these are called the likelihoods for Alice and Bob. And the maximum likelihood estimator is going to pick whichever one of these probabilities is higher. So maximum likelihood estimators are a good choice when we don't know ahead of time the probability the probability of Alice being the source versus Bob ahead of time. So if we think that everyone is more or less equally likely to be the source, maximum likelihood estimation is a good way to go. Okay. And notice that maximum likelihood estimation doesn't say anything about the complexity. Okay, so here we're giving the adversary arbitrary computational complexity. They can take as long as they want to compute this. This is the best estimate that they can make. Right, so alright, so that's what I mean by this maximum likelihood estimator. This is going to be more accurate. This is always going to be more accurate than the first by estimator. It's using more information. So these are the two that we considered. And now finally, I've set up the type of graph that we analyzed, set up the metrics that we looked at, and the types of estimators that we analyzed. Now let's look at some results. Okay, so this table is showing you the probability of detection for both trickle and diffusion under the first timestamp and the maximum likelihood estimators. Now there's two things that I want to highlight here. The first one is that and here the asymptotics are in the degree of our graph, D, the degree of our tree. So as the degree of our graph is growing, this is showing how the probability of detection scales. So the first thing to notice is that for the first timestamp estimator, as our degree grows, our probability of detection is tending to 0. Can anyone think why that might be?
Because you might pick one of the other ones first.
Exactly. So let's say I have like a bazillion friends, and the probability that I send to one of them very quickly and then they relay to the adversary very quickly before I send to the adversary gets higher and higher the more friends I have. Because you basically have a bunch of independent events. Okay, so intuitively, this makes sense. However, if we use the maximum likelihood estimator, this isn't true. Our probability of detection remains bounded away from 0, even as D grows to infinity. So this is really showing you the power of knowing the graph. If you know the graph, you can account for these effects. The other thing to notice, which is of course what we actually set out to answer in this work, is that at least asymptotically, these columns look the same. Okay? And of course, you should always be suspicious when you see asymptotic results because you don't know what the constants are. But it turns out that in this case, the constants actually look pretty similar as well. Okay. So the intuition here is that the symmetry of these two schemes is outweighing local differences in randomness. What I mean by that is, even though trickle is sending, in this random order over its neighboring edges, on average, it's sending in all directions at the same rate. And that's what diffusion is doing as well. And so when you send transactions at the same rate in every direction, your transaction is spreading kind of like a ripple on a pond. And so all the adversary needs to do is to find the center of that ripple to identify the source of your transaction. And so that's the intuition behind all of these attacks. So probably I'm not going to go into detail on this proof sketch, but I don't want to bore you guys to death. But I will give you just a very quick intuition.
which is let's suppose that these yellow nodes are the nodes that have the source at the time of the attack, and these blue guys are the ones that have the message and also reported it to the adversary. So if you look at the neighboring subtrees of the true source, the key point is that each of these neighboring subtrees is going to have approximately the same number of blue nodes. And that's not true for any of the other nodes in the graph. So like this blue node has 1, 0, 3, whereas this one had like 1, 1, and 2, which are approximately the same. And you can show that more formally using a technique called generalized polyerrors, which I will not go into. Okay. So, all right. So these results that I've told you, they're kind of weird in the sense that they were asymptotic in D, the degree of our graph. Why is this a weird result? Why would you be suspicious of that result? Is your graph changing its degree over time?
Shouldn't.
Yeah, maybe a little, but not not large scale. So typically what we're worried about is you're given a graph, you have whatever topology you have, and you want to understand what's the adversary's probability of de-anonymizing a node at any point in time. Does it make sense why that's kind of a disconnect? Okay. Okay, so the results that I gave earlier, they're asymptotic in a property of the graph. So that means as the degree of our regular tree grows and grows and grows, we see how the probability of detection decays. But that's kind of a weird result because in practice your graph topology is not actually changing. It is what it is. It might be changing a little bit, like you might have a few nodes that are changing their peers over time, but in aggregate it's changing at a pretty slow rate compared to the rate at which transactions are propagating. So far so good? So it's kind of weird to give a result that's asymptotic in a property of the graph when the graph isn't really changing over time. You're not expecting the degree to grow to infinity as time goes to infinity. Does that make sense? So to try to understand what actually happens in practice, we turn to simulations. So we started by first simulating our results on trees, on regular trees again. And here we're comparing trickle and diffusion. And the blue line is the theoretical prediction for diffusion. And we see that they're basically identical. Okay, so at least on a tree, we don't expect really any difference at all. But again, this is not super representative because as we said earlier, the Bitcoin graph is not a tree. And here what I'm varying is the number of eavesdropper connections per node. So as the eavesdropper makes more and more connections to each node, their probability of detection is tending closer and closer to 1, which is consistent with our intuition. But so again, this is kind of weird because we're looking at results on trees, whereas the network is not really a tree. So what we tried next was to look at some results on the Bitcoin peer-to-peer graph. So this was a snapshot of the graph taken in 2015, so it's outdated. But basically we simulated trickle and diffusion, and we applied our predictions for a tree that has the same average degree as the graph snapshot that we used. And to my infinite surprise, it actually was a pretty good predictor of the simulation accuracy, simulated de-anonymization accuracy on the real Bitcoin graph as well. And that is presumably because of the fact that you have this locally tree-like property on the Bitcoin peer-to-peer. Okay. So here again, what we're varying on the x-axis is the number of eavesdropper connections. So the more eavesdropper connections you get, the higher your probability of detection gets. Now, on the Bitcoin peer-to-peer graph, we actually do see a little bit of a difference between trickle and diffusion. And remember, lower is better here. We don't want, like for privacy, we want the probability of detection to be low. So it does look like there was some small gain by moving to diffusion. But the problem is as this number of connections grows, that difference gets smaller and smaller. And the other problem is that even for just a few connections, you can get probabilities of detection over 1/2, which is a little alarming. So that kind of wraps up the conclusions from the first part of our research, which suggested to us that diffusion doesn't seem to have significantly better anonymity properties than trickle. Now the caveat here is that in moving to diffusion, they also patched this other thing that Suhas mentioned, where you could basically just force a node to tell you anytime they had a new transaction. So in practice, it did have a good privacy implication, but the properties that we were looking at were more theoretical on these two protocols and trying to compare them. Okay, so we've been going for about 45 minutes, so I wonder, would it be good to take like a 5-minute break and then we can talk about the second part on redesigning the peer-to-peer network? Okay, so before we break, are there any questions on the first part of this talk? Yeah.
I'm curious if you tried with more than 20 connections. Like, because I assume that people like Chainalysis have like 1,000 connections.
I'm sure they do.
Or even more.
Yeah, we didn't. We were limited by my...
No, to each node one. 20, it was 20 connection to each node?
20 to each node,
Oh,
yeah, that's
okay,
right. That's right.
okay.
Yeah.
That makes more sense.
You were
Okay.
already pretty close to
Yeah.
one anyway.
We were pretty close. Yeah, I didn't try more than 20, but...
20 is a lot, yeah.
Yes.
You mentioned like the graphs is more or less the same, but before we also discussed that potentially you could like have a high churn and how you would like have the graph connect to each other. So that would actually be a significant improvement also.
Yeah, that's a great point. So if you have a lot of peer churn in your network, it becomes a lot harder to do some of these more sophisticated attacks. The first spy adversary still works basically perfectly. That doesn't suffer at all from peer churn. So, you know, adding peer churn for privacy is something that we will try to exploit in the next part of the talk. And I think that does help from a privacy standpoint. But for some of these very basic estimators, it doesn't really make much of a difference.
Isn't peer churn the same thing as rotation?
Yeah, peer churn is just when the peers in your peer-to-peer network are coming and going, or like changing their connections, these kinds of things.
The second question I have, I'm not sure, but this doing the diffusion is that you collect all the transactions you get within a specific time frame, and as soon as the timer hits, you send out a multi-inf, or is it like one per inf or transaction?
So I believe you have a per peer timer, and when the timer for, like, let's say if I have a connection with you, when your timer hits, I believe you send an in for like all of the transactions that I've queued up for you.
Pardon me. I didn't quite understand so there's simulation versus the actual topology, but I didn't quite understand the method. Like, what actual topology did you take in comparing the two?
Okay. So
Yeah,
like here. So for the simulation, for the dotted lines, I used a snapshot of the Bitcoin peer-to-peer network measured in 2015 before they made it hard to understand what the graph topology looks like.
Okay.
So this was collected by my colleague Andrew Miller, who had a project that is basically an eavesdropper node. And for the analytical prediction, I used the analytical, for the analytical prediction, I took the theoretical results for a D-regular tree, where D is equal to the average degree of the Bitcoin snapshot graph that we have.
I'm sorry. Could you please recap the difference between trickle and diffusion?
Sure, yeah. So trickle was the like pre-2015 approach that was being used to relay transactions. And this was the one that I kind of goofed up on the modeling. aspect. But it's the way I was modeling it was that you order your peers in some random order, and then on every like k seconds, you'll send it to the next peer. You'll send the message to the next peer in that ordering, in whatever ordering. So it's, you can think of it almost as like a discrete time relaying process.
So you stayed with that, that was close enough, so you stayed with that?
Yeah, I mean, we found out about it after we published the paper,
right,
so we were
yeah.
kind of, our hands were a little bit
Sure.
tied at that point.
So,
But I do believe actually that if you were to change it to what was actually happening in Trickle, you would get similar results, because
every k seconds.
every k seconds you change which peer you're communicating with.
Is there any reason to believe that, from 15 till today, it seems like this is the perfect graph model you found for the actual topology. Is there any reason to believe that would be different today, or do you think it's still?
That's a great question. So the question was, is there any reason to think that between 2015 and today, this predictive model might no longer hold? And the answer is, yeah, some things have happened, I think, in recent years that might make this a less good predictor. One of these is that we're starting to see more supernodes. We're starting to see nodes that are disobeying protocol and making like a bunch of connections. And I think that is, I believe that's happening to an increasing degree, but maybe some of you guys who work on this more regularly, correct me if I'm wrong. But so basically the point is, if you have a lot of nodes that are disobeying protocol and are not just making 8 outbound connections, then it's going to look less tree-like, basically. And so this is one of the things that Andrew Miller found with his eavesdropper node that he was using to try to measure the graph topologies, that you have some nodes that are making way more connections than they're supposed to. Yeah.
I'm curious, how did you do the graph snapshot? Like, it doesn't sound like even like knowing the exact graph right now is that easy.
I think that's true. So back when Andrew collected this, you could, I think there was some trick where you could figure out, if you were connected to a peer, you could figure out who they were connected to. And I think that's been kind of clamped down on now.
It's still very, I think it's still very easy to figure out.
Oh, really? Okay.
Wasn't there some number that like got incremented in a way that you could tell like how many times it had been incremented? It's the paper with Dave Levin.
Sorry, I'm not sure. What was the question?
The Andrew Miller's paper, like topology. I think there was like something in when the transactions were rebroadcast, like there was some number that got incremented, especially that you could, a deterministic way that you could tell like how the hops of the peers.
That might be true. I'm sorry, I don't remember.
That's no longer true.
At the end of the last session, we concluded that diffusion doesn't seem to have significantly better anonymity properties than Trickle. And so some of the key things that I want you guys to take away from that portion of the talk was really how to think about modeling some of these problems if you want to do any kind of theoretical analysis. So often, if you're trying to do something fully general, it can be tempting to make your models really complex and have all the bells and whistles that are actually represented in the real code base. And often these are the kinds of things that are going to make the problem intractable and probably won't be able to show anything. So in our work, we had to do a lot of simplifications down to a model that was pretty simple, but ended up being reasonably representative of the final system. Okay, so after concluding that Trickle and diffusion have more or less the same performance, that really motivated our decision to try to come up with a better design that doesn't have this weakness. So just as a reminder, in this part of the talk, we're going to have a slightly different adversarial model, where we're going to assume that some fraction p of spies are participating in the network. So we call this a botnet adversary. And their identities are unknown. They get to observe whatever metadata comes to them. So they're just regular nodes. So they can see what time they get a transaction from you. They know who they got it from. And these spies are all colluding and are trying to infer the source. And in the beginning, we assume that these spies are honest but curious. So this means they are following protocol and they're using whatever information is available to them from the protocol to try to de-anonymize users. So actually, Matt was saying during lunch that there's some evidence of basically like botnets controlling something like 10% of the Bitcoin peer-to-peer network, which was kind of surprising to me. So it seems like this adversarial model may actually have some grounding in reality. And we also assume for our analysis that these adversarial nodes are uniformly placed in the network. So we're assuming that they're not targeting one particular node, but are kind of uniformly spread out. So, okay, so if these nodes were targeting one particular node, what should they do? Surround it, yeah. So I guess you learned about eclipsing attacks. Was that yesterday? Yeah. So if they were interested in this guy, they should try to basically surround it completely. So whatever it sends, they'll know who it was. But in this case, we're interested in a more broad-scale adversary that's trying to de-anonymize as many people as possible. So this would be the goal of something like analysis, for example. Okay. So our metric for anonymity is actually also going to get a little bit more complicated in this portion. So remember in the previous portion of the talk, we were analyzing the probability of detecting the source. In this portion of the talk, we're going to assume that you have lots of transactions and lots of users. And the adversary's goal is to try to map transactions to users. So the key difference here is that in the previous portion of the talk, we were thinking about one transaction that's spreading. The adversary observes how that transaction spreads and tries to guess the source node. In this case, it's observing a bunch of different spreads, and it can use those different spreads to try to improve its guess. So basically, if we know that each user has one transaction, and so there are n transactions and n users, I know that two transactions are not going to come from the same guy. So I can use somebody else's transaction to actually improve my guess on your transaction, which is kind of disturbing, but it's possible in practice. So what we're going to do here, the adversary is going to design some mapping, M, that maps each transaction to one user. And we're going to define first a metric called recall, which basically just counts how many of these arrows are correct. So in this case, the top arrow is the only one that's correct. So we have a recall of 1/3, 1/3. And I want to point out here that recall is basically the same thing as probability of detection. So this is exactly the same metric that we were analyzing earlier. I've given it a different name here because precision and recall are concepts from the machine learning literature, as well as like it's used in a lot of different domains that typically go together. So that's why I've changed the name. The second metric is precision. Precision is defined as follows. For every correct arrow, I'm going to count the number of total transactions that got mapped to that same guy and assign it a value of 1 over the total number of transactions. So for this red guy, we have a correct arrow, but 3 total transactions mapped to him. So this guy gets a value of 1/3, and these two get a value of 0. We take the average over all 3, so we get 1/9. Okay, so intuitively, precision is trying to ensure that the adversary doesn't just guess, like put all of its guesses on the same user. So it's trying to capture plausible deniability in some sense. Because if the adversary tries to put all of its guesses to the same user, the user can say for any one transaction, well, I couldn't have generated that one because you also said I generated this other one. So you should think of precision as like a plausible deniability. whereas recall is just the raw probability of detecting the source. And recall is more commonly analyzed in the literature, so this is a little bit new, I would say. But I think one key insight is that in practice, adversaries can and will use knowledge about other people's transactions to improve their knowledge of your transactions, or like try to de-anonymize you better. And so precision is trying to capture that. All right, so these are our two metrics, and we want both of them to be as low as possible. So remember we said probability of detection should be low. We also want precision to be low, to have good anonymity. So our goal is to design a distributed flooding protocol that minimizes the maximum precision and recall achievable by a computationally unbounded. A bit of a mouthful, I'll let you stare at this for a second. Okay, so we're trying to minimize the maximum precision and recall. I'm going to try to interpret this goal in a picture for you. So remember, we're looking at two metrics. One is recall, one is precision. The adversary wants to be up here, and we want to be down here for good privacy. And here, P is the fraction of spies in our network. So we started by showing that because of the way we've defined precision and recall, any scheme that you design is going to fall somewhere in this like almond-shaped thing. And that's basically because of the definition of precision and recall. If your recall is really high, by definition, your precision will also be pretty high. So that's why you can't achieve any point in this square. It's always going to be somewhere in this middle region. Now, let's suppose we fix a spreading protocol. Let's say we're thinking about diffusion. Remember, diffusion was the protocol that we talked about in the last half, which is what's used today, where you broadcast transactions to each of your peers with independent, exponentially distributed delays. So diffusion is what's done today. Now let's suppose that we consider every possible estimator that the adversary can think of. So remember, an estimator is just taking a mapping from transactions to users. Each of those estimators is going to be some point in this almond. And if you cycle over every possible estimator, you'll basically trace out a region. So this region should be filled in. You trace out a region in this space. And the size of that region is basically telling you how good is your spreading mechanism, or how private is your spreading mechanism. So the worst possible spreading mechanism we could think of would take up this whole region, and the best possible would be just like a point down here. Does that make sense? So when we started this work, one thing that people like to do in theory circles is to try to prove converse bounds, or like lower bounds on whatever property you're trying to reason about. So in this case, we want to know what is the minimum possible precision and recall that we can hope for over any spreading. So we started by showing that no matter what spreading protocol you use, they are always going to have a maximum recall that is greater than or equal to P, where P is our fraction of spies. So this means no matter what spreading protocol we use, this region has to extend to at least this vertical dotted line. It's going to be to the right of it. The second result is that no matter what protocol you choose, your maximum precision is always going to be at least P squared. So the top part of this region is always going to be above the horizontal dotted line. And intuitively, this is, so the recall result is a lot easier to reason about, but intuitively this is happening because if I send my message to some random person, with probability P, they're going to be a spy. So if they just use the first spy estimator, they're going to be right at least P fraction of the time. So that's telling us why this maximum recall has to be at least P. It's kind of a similar intuition for precision. Yeah. Exactly, yeah, yeah. So to make this kind of visual, every spreading algorithm that we look at is going to have at least one point in this gray region. In other words, the best possible region we can hope for is this green triangle, this green little nubbin. So that's our goal. Our goal is to find a spreading protocol whose region looks like the green triangle. If that's all you take away from this slide, just green triangle. So all of this is really just interpreting our metric and trying to understand what is the problem. Now, how do we hope to achieve this? Well, intuitively, there's two properties that we really want. The first one is asymmetry. So if you guys remember from the previous half of this talk, when we said that trickle and diffusion seem to both be bad, and the reason for that is that they're sending messages in every direction at roughly the same rate. And by every direction, I mean every direction on the graph. So intuitively, the way to improve your privacy is to break that symmetry. So if you send it faster in one direction than the other, it becomes harder for the adversary to figure out where it originated. So we're looking for asymmetry. The other thing we're looking for is mixing. And here, I don't mean mixing in the sense of like a mixed network. I mean it in the following sense. So let's suppose we have 4 honest nodes in a row. They're all sending their messages to the right. And we have the spy node at the end collecting them. So the spy node is going to get 4 transactions. One from 1, one from 2, 3, 4. And from the adversary's standpoint, from the spy standpoint, all 4 of these messages basically look the same because it doesn't know when any of them originated. So the metadata that this spy gets is just the time when the message was delivered to him and from whom. But it's only getting delivered through this last edge. So that doesn't really differentiate any of the transactions. So when I say mixing, I mean whatever the spy sees, it should have a hard time telling if it actually came from node 4 or if it came from node 1 or like who it came from. So intuitively, these are the two properties we're looking for. And we have a few knobs that we can control to try to make that happen. The first knob is the spreading protocol. So given a graph, how do we spread content over it? And as we've talked about a few times today, currently that's done via diffusion. The second knob that we have is the graph topology. So right now we have this construction where each node is picking up to 8 outbound peers. But in principle, maybe you could change the peer-to-peer topology to make it more privacy preserving, potentially. So today we'll use this approximately regular construction. And the third property is dynamicity. So how often does the graph change? As we mentioned earlier, this is changing on a fairly slow time scale. So most transactions take seconds to propagate, maybe like tens of seconds. Whereas the graph is changing on a slower time scale than that. So one option would be to have the graph change at a faster rate to make it harder for the adversary to learn the graph, which in turn gives you better privacy. That's something that we've also touched on already today. So in Dandelion, we're going to touch on all 3 of these properties. Let me start with the spreading protocol. The Dandelion spreading protocol is very simple. the idea is that if you start with, let's say this node is the source. So the source, instead of spreading the message to all of its neighbors, it's going to choose just one. It sends the message to its one neighbor, and that one neighbor is going to pick one of its neighbors and forward the message. And this happens for a random number of hops. So this is called the stem phase. And after that random number of hops, all of a sudden we switch into the fluff phase. And here we start doing diffusion again. So this guy spreads it to all of its neighbors, and they spread it to their neighbors. And so this, we call this dandelion because the spreading pattern looks like a dandelion seed. So, okay, so why is dandelion spreading a good thing to do? Well, it turns out that it has an optimally low maximum recall of p plus some terms that are big O of 1 over n. N here's the number of nodes in the network. As your network grows, you get closer and closer to that lower bound on precision. So remember, our lower bound was exactly. So this is good because it means, like earlier we were reasoning about these regions. We had two metrics that we were trying to optimize. And optimizing two metrics is a pain. We want to optimize one metric. So this tells us that if we constrain ourselves to dandelion spreading, we can basically only worry about precision. Because no matter what graph topology we apply this to, we're going to get a recall of p. Here I'm assuming the graph is connected. Okay, so that nails down the spreading mechanism. The two other knobs we had were graph topology and dynamicity. So for our graph topology, we think about having basically two like overlay graphs. The blue lines here are going to represent the regular P2P network, whatever currently exists. In addition to that, we have these black lines which represent the anonymity graph. And this is what the stem is going to propagate over. So just to show you how that works, if a transaction comes in at one of the nodes, it propagates clockwise over this line anonymity graph for some random number of hops. And then once the stem phase is over, it gets diffused over the rest of the graph. This diffusion is ensuring that the transaction spreads quickly enough. Now, if a second transaction comes in, it's going to propagate clockwise over the same anonymity graph. So this is actually important. They should be propagating over the same line until the fluff phase starts. So this is the topology that we have in mind. And I'll talk later a little bit about how to construct this topology. Finally, the third property that we talked about is dynamicity. So here we want to change this anonymity graph pretty frequently. And the reason for that is so that the adversary doesn't really know the graph very well. So the adversary is always going to know its neighboring nodes. That's impossible to fix. You can't get around that. But what we don't want the adversary to know is what's in the areas that are uncharted. What's in the areas that it's not connected to. And so for that, we're going to change this line graph periodically. So the Dandelion network policy consists of dandelion spreading, line graph topology, and fairly high dynamicity. Okay. So here in our analysis, we kind of assumed away some of the properties of this high dynamicity and just assumed that the adversary doesn't know the structure of the line graph in our initial analysis. Later, we extended this to when the adversary does know the topology. But in our first paper on the topic, we just assumed that the adversary does not. And in that case, you can show that Dandelion has a near optimal maximum precision that looks like p squared times log p. Okay. And remember, our lower bound on precision was p squared. Here p is less than 1, so p squared is smaller than p. And so here in our precision, we have this p² term times a logarithmic term. We're a log factor away from optimal. Now, if we interpret this in terms of the picture that I showed you earlier, this little blue region shows you the anonymity region for Dandelion. And the red one shows you a lower bound on the region for diffusion. It could actually be larger. This was obtained through simulation. And the yellow one is what would happen if you just flooded to all of your nodes with no delay. So that's terrible. You shouldn't do that. So this is showing us that basically we're pretty close to the green triangle. Remember our green triangle? Yeah. So Dandelion seems to have some good theoretical properties, but why is it good? I'm going to give you a little bit more intuition as to why this should be the right thing to do. And to try to give you some of this intuition, I'm going to talk about some ideas that don't work, that we thought would work. So the first thing we tried was a tree. So let's suppose, okay, I mean there's a bunch of reasons why you don't want to structure your P2P network as a tree, potentially, but we thought maybe for privacy this would be a good idea. So let's suppose you structure your network as a tree, and every node is passing their transactions up the tree towards the root. This turns out to have a precision that looks like O of P. So here P is, remember P is larger than P squared. We want P squared, we're getting P. And the reason this is happening is because trees have too many leaves. So basically what happens is for every red node in the second to last layer, that red node is able to perfectly de-anonymize 2 leaves, or however many leaves are in your tree. And because you have a constant fraction of red nodes in your second to last layer, basically these red nodes are doing a ton of damage. So this gives us the intuition that we want a graph topology that doesn't have too many leaves in it. The other type of topology that we actually thought would be really good is a complete graph. So here everyone is connected to everyone. Again, there are reasons why you would not want your P2P network maybe to be a complete graph, but just for the sake of analysis, let's entertain this idea. And this turns out to also have suboptimal precision. So the intuition here is a little bit subtle. Remember we talked about wanting to have mixing. So we want different transactions to take the same path in the network so that they look similar to a spy. What happens in a complete graph is that there are so many paths that the probability of 2 transactions taking the same path is actually very low. So this red node, if it's observing transactions from different nodes in the network, the probability of those transactions coming in on the exact same edge is actually pretty small. So this gives us an intuition as to what's wrong with complete graphs. They have too many paths internally, too many edges. So what we want is a topology that has few leaves and not too many paths. So a line graph kind of ticks both of those boxes. It has, well, so what I showed you was a cycle graph, so it has no leaves, and it has only one path internally. So that's intuitively why Dandelion is getting good anonymity. Basically, what we were thinking is that you would have every node would choose one of their outbound connections to be their Dandelion edge, or like 2 or whatever. Actually, I've only talked about line graphs for now. So you choose one of your outbound connections as your Dandelion connection, and anytime you either receive a message that's in stem phase, or anytime you generate a transaction, you send it over that Dandelion edge. And along with that message, each node in the stem is flipping a weighted coin. So like with probability, I don't know, 0.1, they start the fluff phase. With probability 0.9, they relay it to their Dandelion outbound edge. So the number 1 most common FAQ is, why don't you just connect through Tor? So the idea here would be that if Alice is broadcasting her transaction, she connects through Tor to some other random node, and the other random node broadcasts her transaction. So this is a reasonable thing to do, and as Suhas mentioned, if you're worried about targeted attacks, this is probably what you should be doing. One downside is that when you're relying on these kinds of third-party services, basically it's only the people who are already really worried about privacy that will be using this solution. So ideally, if you're trying to build a system that is protecting everybody's privacy, there should be something built into the system that is protecting that. And so that's kind of the spirit in which thinking about Dandelion. It's system internal. And the other thing that people ask is I2P integration. So for those of you who haven't heard of I2P, it's it's conceptually kind of similar to Tor. So you're basically building a cryptographic tunnel to another node, and the end result is that this other node gets it, and the tunneling is done within the peer-to-peer network that you're looking at. But these guys are onion routing the transaction. So I'm oversimplifying things a little bit here, but the point is this is not relying on an external service. So for example, Monero is doing this integration right now, and this also addresses the same problem that we're trying to protect against. So this would be another way of doing it. The only potential downside that I can see with this kind of approach is that it may take a little bit longer to implement, just because implementing cryptography correctly is pretty hard. And it can take a while to do it right and to build up the necessary expertise. So a lot of projects that we've talked to maybe didn't feel comfortable or felt that this integrating I2P would be too big of a change to their code base, and so they didn't want to do that. But they felt that Dandelion was a simple enough protocol that they were willing to do that. So maybe a trade-off in terms of just ease of implementation. All right, so now let's talk about some of these practical considerations that you all have been asking. Very good questions. So what do you think would be one of the trade-offs that you want to make when you're thinking about whether to deploy Dandelion or not? What's one of the downsides that you can potentially see? Latency. So when you have this initial stem phase, it takes longer for the transaction to reach all of the other nodes. This could be a problem if you want your transaction to get added as quickly as possible to the ledger. So this is kind of an old plot. This is from 2013, but it's showing a PDF of the time to first transaction citing. So here on the x-axis, we have the number of seconds until each node first saw a given transaction, and this is the density or the PMF of that. So what we see is that on average, nodes are taking between 10 and 20 seconds to see a transaction for the first time. So this is actually kind of slow, and you can. So I guess this measurement was taken when Trickle was still being used. But even now, if you think about diffusion, if each edge has a delay of about 2.5 seconds, these numbers don't seem that far off. And I'm sure there are more recent numbers that we can hear about later. But the point is, this is taking on the order of 10 to 20 seconds. So the amount of added latency that we can tolerate is maybe on the order of a couple of seconds. That's probably the most you would want to add. So to try to understand what is the overhead of adding Dandelion, another thing to point out here is that if you are running Dandelion, you don't have to use that 2.5 second delay as you're relaying it. So you can use that to lengthen your stem without adding too much latency overhead. So we implemented this and tried running some Dandelion nodes in the Bitcoin network and tried to measure, as a function of our path length, of our stem length, how much time it took to reach 10% of nodes in the network. And we took this measurement, again, using Andrew Miller's Coinscope device. So we waited to see, we're connected to some 10% of nodes, or we're connected to a bunch of nodes, and we waited until 10% of them had relayed the transaction to the eavesdropper. And so what we see here, so when path length is 0, that's basically just regular diffusion. And so as you scale from like 0 hops to about 10 hops, you're adding a couple of seconds on average to the latency required to reach the first 10% of nodes, which suggests that you can probably tolerate about 10 hops without adding too much latency. Again, this is not an exact science. We're really like ballparking numbers here. So how does the path length affect your privacy guarantee? So in the analysis that we did, we assumed infinite path length. Okay? But a key point here is that as soon as you reach a SPI node, everything that happens afterwards is not going to help your privacy. So if you have like 10% SPIs in your network, then in expectation, it'll take you 10 hops to reach one of those SPIs, and then after that, you're not getting any more privacy guarantee. So even though our analysis assumed infinite path length, in practice, the amount of path length that is actually contributing to your privacy is much shorter. So based on these measurements, as kind of a ballpark figure, we chose 0.1 as our probability, so that on average, you'll have a path length of about 10. Another question that you asked, thank you, is you don't actually know in this protocol if your message will get diffused. So let's suppose this was our stem, but this guy is evil. Okay, so he's going to drop our message. I'm not going to forward it. In the protocol that I've described to you so far, there's basically nothing protecting you. Your transaction is never going to reach the rest of the network. So what we did in our reference implementation was to implement random timers on each of the nodes in the stem. And once one of these timers goes off, these are also exponentially distributed timers. Once one of them goes off, it starts diffusing the message. And similarly, once this guy's timer goes off, he'll start diffusing the message and so forth. This is true for all of the nodes in the stem graph. And this is really, obviously this is going to have some impact on your privacy, and we have a little bit of analysis on this in our paper, Dandelion++. But this is really a trade-off because you can't sacrifice robustness. Robustness always matters more than privacy in these kinds of systems. So, so you have to have some kind of backup plan if you have this kind of an attack. Yeah. So if you see that the fluff phase has started and you receive a message in fluff phase, then you cancel your timer. I titled this slide incorrectly, so apologies for that. But remember, we talked about changing your routes. So periodically, you're going to change your Dandelion outbound edge. One key question that I believe came up when the Bitcoin Core team started thinking about what it would take to actually deploy this is, what happens if you change your route, but you already sent some transactions on the first path, and then you have some dependent transactions that you're sending on the second path, on the new path? What do you do then? We created a big mess. So the solution that we were thinking about was to retransmit the the earlier transactions on the new path as well, which seems to solve the problem. But then there's this nasty little problem of RBF, by fee. So even if you send the updated fee down the new path, there are some nodes on the old path that still have the old fee. So my understanding is that this is one of the big roadblocks at the moment, and I would love to talk about this more with you all later. So in practice, even though the protocol seems really simple, it turned out to be more complex than we expected when we first were designing this and thinking about it. And a final practical challenge that we looked at in our Dandelion++ paper is that in practice, you you're not going to be able to get everyone to deploy on day one. So in practice, you're going to have some subset of nodes that are maybe early adopters, and then gradually maybe more people will join on. And so it's really important when you're designing these kinds of protocols to make sure that everything is backwards compatible, and that if you deploy something, it's not going to break privacy for the other people or break robustness for the other people. So that's partially why we implemented in our reference implementation the flag in the way we did, so that it won't break nodes that are not running Dandelion. They'll just view it as another transaction that they should broadcast. But we also did some analysis on the privacy guarantees and showed that as the fraction of honest nodes adopting Dandelion grows from 0 to 1, your expected recall, an upper bound on your expected recall, also gets closer and closer to your lower bound of P. Remember, P was the recall that we expect to get for Dandelion. So this has a nice property, which is that it's kind of smooth degradation as fewer and fewer nodes actually adopt your protocol. But even if one node adopts it, they get some privacy benefit, and as more nodes adopt it, you get more and more benefit, like herd effect. So the end story seems to be that complexity and robustness, or the trade-off between complexity and robustness seems to be a barrier. So kind of unclear if this will get adopted, but we would like to try to see if we can make something, I would like to try to see if something can be made workable. So one thing that I've been thinking about in the last couple of months is Dandelion Lite. So this is really just like a one-hop version of Dandelion. So instead of having this random number of hops in your stem, you just send it over one hop and then diffuse it. And the second guy has a transaction, send it over one hop and diffuse it. And it turns out that this very simple scheme has similar privacy guarantees to regular Dandelion if you assume that the adversary knows the graph. If you assume that the adversary does not know the graph, then old Dandelion still has stronger privacy guarantees. So you're giving up something in terms of privacy, but it's a much simpler scheme. And so one thing that is still missing from this is simulations, which I would like to run. If anyone's interested, oh, so here with this one hop, you don't know if you're receiving a diffusion message or a stem message. So you basically include no flag, nothing. That's the difference, yeah. You might still think of it as a dedicated connection, but you won't like set a flag or anything. Like if I connect to you, you wouldn't know that you're my Dandelion connection. Here's how it would work. I draw some random delay. I send it to you. And then as soon as my delay timer ticks, then I start diffusing. So it if you decide to drop it, I'm still broadcasting it. If you don't decide to drop it, I get some small. Here's one naive thing that you could do. You could say, I'm only going to connect to nodes that are running Dandelion. Now, what's the adversary going to do? They're going to say, I'm running Dandelion, connect to me. So this blue curve is what happens if you do this announcement, or if you try to only connect to Dandelion nodes. And the adversary is basically lying, and they're saying that we're running Dandelion and nobody else is. So then you're going to get de-anonymized 100% of the time, or close to it. So this pink region is what happens if you just make your connections independently. You don't care if they support Dandelion or not. And so if they do support Dandelion, then they'll relay it. If they don't support it, then they'll just diffuse it when they receive your message. So this clearly seems to be the better operating point. So in all of our analysis, we assume that the adversary knows which nodes are running Dandelion. So we already abstracted away that inference part of it, yeah. I wanted to close off with this kind of interesting plot, which came out of Princeton in 2017, Ryan and Moser. And so this is showing you a bunch of privacy technologies that have emerged in the blockchain space. So here on the horizontal axis, we have the date of invention. And on the vertical axis, we have the strength of guarantees, ranging from obfuscation to cryptographic. Okay, so obviously, this is not a precise scale. But they've ranked different protocols in terms of what the strength of their guarantees are. And what's interesting about this is they've colored the different approaches based on whether they are used in Bitcoin. So that's orange. Used in altcoins is blue, so these ones up top, and gray is not used at all. So what's kind of fascinating about this is that none of the cryptographic approaches are actually used in Bitcoin. Actually, this might be a little bit out of date. Maybe some of these gray ones are used nowadays in a few altcoins. But the way I read this was that a lot of the cryptographic approaches are like complex. They're a little bit too complex to actually get adopted. It takes too much overhead. I would love to hear perspective from the people actually developing this. But so our objective in this work was to try to work in the obfuscation territory, but try to max out your privacy guarantees within those constraints. And so far we've had interest from a few different venues. So Dandelion's currently implemented in Grin and Beam, which are two like privacy-focused altcoins. BitMessage is a peer-to-peer messaging service that is supposed to protect your privacy. And so Dandelion isn't really cryptocurrency specific. It's more of just like a messaging, one-to-all messaging service. And so the way BitMessage works is by broadcasting messages to everyone. And so this was kind of an oddly good fit. So that kind of wraps up this presentation. So 3 take-home messages that I hope you get from this talk. One is that Bitcoin's peer-to-peer network has kind of poor anonymity guarantees because of the randomization in the way that transactions propagate. So moving from trickle to diffusion didn't help. So here should be a star here, which is that actually it did help because it was closing down this important bug. So this is more from the perspective of like the theoretical analysis that we did. And third, Dandelion may be a lightweight solution for certain classes of adversaries. And I want to highlight here that, again, that the adversarial models that we're considering are really aggregate scale for parties that are trying to de-anonymize lots of parties. The tool is really not designed to protect against targeted attacks. So with that, thank you for your attention. This is our BIP if you're interested. And yeah, I'll take any more questions. There were a lot of issues where not just DOS, but like when we actually started trying to implement this, a lot of people from the Bitcoin core team were bringing up ways that an adversary could potentially try to probe whether a node has a transaction in Dandelion mode. And so that led to a lot of additional complexity. So like at some point we were keeping like per peer mempools, basically, Dandelion mempools. And which seems like it may be not feasible in the long term. So I think there's a lot of DOS protections, and making this compatible with all of them is, I think, tricky. That's something that I don't think we've fully figured out yet. My understanding, which could be off, is that Erlay sends transactions along your outbound edges normally, and with respect to the inbound edges does this set reconciliation. Is that correct? Okay. So notice that in Dandelion, you're really only relaying on your outbound edges. So that is completely compatible with Erlay because Erlay is only doing something different with respect to your inbound edges. Yeah, one is efficiency, one is privacy. So I think what this would look like is you would do Dandelion for like some number of hops, whatever that ends up being, until you enter the diffusion phase, and then once you enter diffusion, then you basically do Erlay. Questions? Thanks, guys.